Okay, hi students. Today I'm going to talk about virtual memory. Sorry, I made a typo in the first page of the slides. It should be lecture 11 rather than 21. Today we have a relatively thick material. So we need to talk about demand paging, and then it's copy on write and page replacement. Algorithms, which is the most important part of the lecture, and after that we're going to talk about some more materials. So before that, I just want to quickly go through um, the the lecture of last week. So last week the most important picture is over here. Um, we learned two new concepts, which are the logical memory and physical memory. So physical memory is pretty much like the actual RAM that you have on your computer. While the virtual memory or logical memory is something of imagination. It's an imagination of the memory space, and so whenever we are giving a logical address, so we need to say refer to the MMU, which are the memory map unit of our operating system, to translate the virtual address into physical address, so that we can go to the exact location in our physical memory and retrieve the data for us, or the files for us. So, and then we learn two different ways of memory space allocation, which are contiguous and uncontiguous allocation. In terms of contiguous allocation, so we definitely say a big problem with that, which is so eventually around 1/3 of the total memory space will be filled with small holes that cannot fit anything. To fix the problem, then people propose uncontiguous allocation, which means that, so if we have a process, and which includes multiple pages or frames, so we can actually allocate uncontiguous frames in the physical memory to that process. And then this gives us two topics, which are called paging and segmentation. And this is what we learned from last week. And today, first, let's let's get some background. So far, we only consider the case, say if one process is in execution, all of the actually the entire logical space is already placed in the memory. So this is pretty much like. So first, let's talk about what is the difference between virtual memory and a physical memory. If we take Montclair as an example, the campus that we have is pretty much the physical memory that Montclair has. So if we have some students or faculty who come to the campus, they have to be allocated some space in the campus, either a classroom or a office. However, as you know, that the campus space is quite limited, so which can only host around 6,000 people at the same time. So actually, if more than 6,000 people come to campus at the same time, there will be a big trouble. Someone will spend hours of time in order to find a parking space, while some other people may not even find any seats in the campus. So and then to afford to have more students, Montclair devises some strategy, which are some kind of like online courses, and they also try to students on different to come on different dates. Say some students come on Mondays, Thursdays, while other students come on Tuesdays and Fridays, in order to split the human traffic. So with this kind of strategy, Montclair actually has more than 20,000 students registered. So you can take this as the virtual memory space of Montclair. So it's not a real it's just something like imagination. It's definitely bigger. Usually the virtual memory space, the size of the virtual memory space is definitely much larger than the physical memory space. So it gives us a way of imagination, saying that okay, so let's assume that we have this much of space of memory, but actually it's not. The physical memory is only like 6,000 people, or for example 16 gigabytes. So far we only considered the case, say, if we have a process and the process has a virtual memory space, no matter how large is the virtual memory space, we assume that okay, all of them, all this space has already been placed in memory in order for the process to be executed. However, this may give us some big problem because, say, one limitation is that okay, the program size or the process the memory space size of the process must be smaller than the physical memory size. For example, if you have a Chromebook which only has 2 gigabytes memory, so if we use this strategy, it means that any process that you execute cannot be larger than 2 gigabytes in size, and which is not, I would say, is not this is not practical especially say you want to watch a movie, or say you want to play some video games. And the other problem is that okay, the memory space is not fully utilized. and because for example, if we consider the next program, the ls command. So the ls command provided by Linux, as we know, it basically lists the directory contents. So, and the beauty of this command is that it comes with different options. Say we have -l, -a, -b, and -c. Different options means that it's like a specific parameter of this function. So if you choose a kind of parameter, basically it shows the files or directory in a relatively different way. So and but actually most of the options are rarely used by users. So if we load all the memory all the program into our memory in order to execute the ls command, so this will result in, let's say, 90% or 80% of the process memory space is never utilized because we don't use those very complicated options in practice. And this leads to a waste of the memory space. And so then people come up with a different design, saying that okay, if you want to execute a process, it is not necessary to load all the virtual memory space of the process into the physical memory. And this give us a lot of flexibility because we don't have the size limit on the program, and also we can so if we are only giving a relatively small physical memory, so we can load multiple the parts of multiple processes into the physical memory, so that we got multi-programming. If you remember what is multi-programming, and then so it saves us the I/O time. Which definitely improves the efficiency of the execution. So virtual memory basically provides us a way to separate the physical memory space into logical memory. Okay, and this is very important for programmers, because as a programmer, what we do is that okay, we assume that okay, when we write the programs, we don't need to worry about the physical memory space. We just assume okay, the program that we write, when it is loaded into memory, okay, it has a virtual memory space. No matter all of the virtual memory space is allocated into the physical memory, or say only a part of it is loaded into into the physical memory. We don't worry about that. We just assume that everything in a virtual memory space is ready for use, and actually it is the operating system who just does this kind of like memory management for us. So it's kind of like, okay, we with the concept of virtual memory, we as the programmers can fully utilize the memory management utility of the operating system. And when we are developing our programs, we're kind of like worry free about the physical memory space, and which I would say erases, removes a lot of headaches from us. So if you have some background with or experience with C programming, okay, you probably know what I'm talking about, because in C programming, the most common error from your programs are called segmentation fault. Segmentation fault means memory fault. There is a crash in the physical memory, and it's very hard to debug this kind of bugs. So okay, and the benefits of virtual memory brings a lot of benefits. So we can execute programs whose size can be a lot of times larger than the physical memory space, and programs do not need to worry about the physical memory. And a side effect is that it allows the files and memories to be shared among multiple processes. And probably if you have a good memory, you probably remember, okay, when we were talking about interprocess communication, we said that one of the three ways of interprocess communication is just shared memory, right? So we basically create a shared memory space between two processes. And actually, with the help of virtual memory, so we have a different way of to create the shared memory space between two processes, and it's relatively easier than the previous approach. So okay, and so this is some background that knowledge. And also, okay, this figure is relatively important. So on the left hand side, we have a virtual memory space of a process. So say this virtual memory space can be very large. And actually, if you use it depends on the operating system, what kind of operating system that you are running. So mostly, so basically, we have two different types of operating systems, which are say here 32 bits operating system or 64 bits OS. Okay, so if you use 32 bits OS, it means that, okay, the virtual memory space, the size of the virtual memory space is this 2 to the power of 32 say bytes. So 2 to the power of 32 bytes is like 4 gigabytes. Okay, so if you are running on a operating system on a 32 bits operating system, so the largest virtual memory space that you can have is this 4 gigabytes, which means what? Which means even though you have a 8 gigabytes RAM or 16 gigabytes RAM, you can only use four out of them, and which causes a big waste of the of your physical memory space. And so this is the reason why, say, starting from maybe 10 years ago, Microsoft is pushing for 64 bits operating systems. And let's say what's the difference between 32 and 64 bits operating systems. If you use 64 bits operating systems, the largest size of the virtual memory space is this. Okay, it is 2 to the power of 64. And if you ask me, okay, how large is this, I would say it is around this number. It is around 16 million. It is around 16 million gigabytes. Okay, so the largest memory space that you can have is 16 million gigabytes, and this gives us a lot of flexibility when we are when we're developing programs, because basically if you are say responsible for a bigger program, say developing a big video game, literally your program can be as large as this number, and nowadays we don't reach this number yet. None of us reach this number yet, but yes, someday it's possible that we, with the reduction in the price of the storage device, probably we are going to enter this stage. So this is the difference between them. Okay, and so let's continue. Okay, so next, so on the left hand side we have the virtual memory space. Usually the virtual memory space is definitely larger than the physical memory. So then here it is the memory map unit. So this is the MMU, and on the right it is the physical memory. So it could be like say 4 gigabytes, 8 gigabytes, or 16 gigabytes. And on the rightmost place it is our disk. So so when we have a process, when we have a process, it's possible that we only load a part of its virtual memory space into the physical memory. So for example, it's possible that we only load page 1, page 2 into the physical memory, while page 0, page 2 in the physical memory, while page 0 is still on the hard drive. So then with the help of a memory map unit, we will be able to tell, okay, which virtual memory page is loaded in the physical memory and which are still on the hard drive, so that when we want to refer to them, so our operating system knows, okay, where to get them. If, for example, if page 0 is in a physical memory, the memory map unit may tell you, okay, go to this corresponding place to find your page 0, and go to this place to find your page 2. Well, if say, okay, if the finds page 1 is not on the is not loaded into the physical memory, it may say, okay, go to this place of your hard drive to find it. So this is the diagram that shows how does the virtual memory space work. And so this one, okay, you may be familiar with this page. So previously, when we talk about the process memory space, actually at that time we were talking about the physical memory space of a process memory, but here we can extend it to virtual memory space of a process. It includes code, data, heap, and stack. So this diagram tells it basically is what I talked about two pages earlier. So the memory map unit can help us do the address translation if the virtual page is loaded into memory, or if it's not in the memory, it can direct us to the disk address in order to find it. So next, let's talk about demand paging. So demand paging means what? It means that we only load certain pages of a process into the physical memory when they are necessary to be loaded in order to be executed, for the program to be executed. And this is this is demand paging. So with demand paging, so it can happen. The swiping can happen when certain pages of a program need to be or of a certain process needs to be swapped in. So then say if the physical memory space is full, this is the physical memory space. If it's full, then so we need to say when some new page needs to be loaded in, we need to kick some page out and bring the new pages in. So and this is where the swapping happens or page fault happens. And but the operating system needs to know, okay, if a virtual page is loaded into memory or not. And so this is done by setting a valid bit table in the page table of the process. So if the valid bit basically is a bit, it can be only be 0 or 1. So here we just use I and V to stand for 0 and 1. So if it equals to I, it means that it's invalid, meaning that the page is not in the physical memory. Or if it's V, it means that it's already in the memory. So you can think about the valid bit as this way. Okay, say we have 20,000 students at Montclair. So at any single time, every student is associated with a bit. If the bit is I, it means that this student is not on campus. While if this bit equals to V, then it means that the student is on campus. So so this is how the page table looks with the valid bit. So here we can say that, okay, if within this virtual memory space of the process, it has 8 pages. Okay, it has 8 pages, but only 3 of them are loaded into memory. Here we can say only page 0, page 2, and page 5 are loaded into memory, and because only these pages have a valid bit of V, while all the other pages have a I in their valid bit. So it means that the other 5 pages are not in the memory. So and here you can and here we can see that, okay, in the page table it tells us, okay, the 0th virtual page is in a 4th place, 4th frame of the physical memory. So if we go to the fourth frame of the virtual memory, we can find the content A, which is the same as this one. Okay, and then so here we have for the third, actually for the virtual page with the index 2, it has it's located in the 6th frame in the physical memory. So here if we go to the physical frame with an index number 6, we can find the corresponding content, which is the C. Okay, and similarly we can find it for the 5th page. So it is at this place. Okay, while all the other pages are still on the memory. Say we have B, D, E, G, and H. These pages are still in the hard drive. And here you may wonder, okay, how come that ACF, these pages are still on the hard drive? This is because so we just copied the information from ACF to the memory, okay, and their original copy are still located on the hard drive. So yes, the access to a page with an invalid bit, it definitely causes a page fault. If you remember, if you remember, a page fault means that so we are referring to a page which does not exist in the physical memory, so that we need to do a swap, a page swap, and it takes time. So okay, and this diagram shows the procedure when a page fault happens with demand paging. So in the first phase, okay, we so we are going to refer to the page, and so we go to the page table and we find an invalid bit, so which sends out a signal to the operating system saying that, okay, the execution of this process must be interrupted because it is referring to a page which does not exist in the memory. So there is a page fault, and then we need to swap some page in, and there is an I/O which needs to be done. So this process has to wait. So we go to the page we find the corresponding page in the hard drive and load it into physical memory. Okay, so this we find a free frame in a physical memory and load the page in, and then we reset the page table by setting the valid bit from I to V, and then we can just let the process go from the waiting status to waiting state to the ready state, so that it has a chance to grab the CPU again. Okay, and here we have a formula to help us calculate the effective access time of a page. So for example, okay, within a program, the probability of go to getting a page fault is p, and so with this likelihood there is a page fault. So if a page fault happens, we definitely need to do something called page page swapping, and takes time, and so the time to do it is called page fault time. Okay, well, if with 1 minus p likelihood we don't get a page fault, so we just directly access the page from the physical memory, then there is a time called MA, meaning this. MA is the short for memory access time. So on average, if we calculate, okay, what is the expected amount of time for us to refer to a page, if the page fault probability is p, then this is the equation. So it is 1 minus p times the memory access time, and p times the page fault time. So yes, here we can do some numbers. So for example, if the memory access time is just 200 nanoseconds, while the page fault service time is 8 milliseconds. Here you need to understand, okay, 1 millisecond is 1 millisecond is equivalent to 8 million nanoseconds. Okay, so in order for us to calculate the effective access time, if we just replace MA with 200 and the page fault service time with 8 million, then the final result is this. Okay, 200 plus 7999 800 times p. So here you can see that, okay, definitely if we have a small p, then the effective access time is going to be relatively small, very close to 200. However, if we have a large p, say p is like 0.9, then this number is going to be very close to 8 milliseconds, and this is very large. So here we can definitely tell that, okay, so in order to guarantee that we have a small effective access time, then we should have definitely make sure that the page fault rate is very low. So then how to do that? Okay, so there are some strategies to reduce our effective access time. So one of them is called copy on write. So copy on write means this. When previously we say that when we call the fork process, when we call the fork system call, if we are in a parent process and the parent process calls fork, so here when it calls fork, what it does is that it creates a child process, and then we still have the parent process. The child process needs to copy everything from the parent, copy all the memory space from its parent, so it has exactly the same variables as the parent. So this can cause a big delay in the execution speed. So those operating system designers come up with a strategy called copy on write. So what this strategy does is that initially the child memory space share the same physical memory space with the parent. So what does that mean? So for example, if this is our memory, if this is our physical memory, okay, this is our RAM, and these are the pages, page 0 and page 1, that are occupied by the parent process. So on the left hand side, we have the parent process. And this is page table. This is the parent process page table. So it says, okay, the 0th page in the parent process is located in, say, this index is, let's say, 2, this is 4, is located at the physical memory frame whose index is 2, and we have a valid bit. And the first page with index 1 is located at the 4th frame in the physical memory, and it also has a valid bit. So okay, so this is the way to do the reference. Okay, so when this parent process called fork system call, so it creates a new child process. The child process is going to do what? It is going to copy its parent process page table. Instead of copying the physical memory space of its parent, it just copies the page table. So it says, okay, my 0th page is at the 2nd frame of the memory, and my page with the index 1 is also at the 4th page, 4th frame of the physical memory. So okay, both the parent and the child refer to the same physical memory space, and this is what does the copy on write strategy do. So in this way, it avoids just copying the actual physical memory space of the parent process, and which saves a lot of time. And nowadays this technique is adopted by every Windows and Linux operating system except for SE Linux. So and this is what I'm talking about previously. We have two processes here. You can say you can take the left hand side as the parent and the right hand side as the child. Okay, they refer to the same physical memory frames. So and then this is one way of reducing the effective access time. So and the other way to do that is to come up with a better page replacement strategy. So let's see what does that do. Okay, so here when suppose here, okay, we are executing a program. So we are executing a program. The user one is executing a process, and PC means program counter. So we are actually executing this page in its program in a process. This page asks us to load M. So if you check what is load M, M is on the third page, is on the 4th page of this virtual memory space. But if we go to the its page table, we will find, okay, an invalid bit for this page, meaning that this page is not in the memory. So we need to it's not in the physical memory. So we need to do some swapping. There is a page fault, and we probably need to do some swapping. So or page replacement. So here you can say that, okay, in the this physical memory is already full. So every frame is occupied. So in this case, in order for us to load the page from disk to the physical memory, we definitely need to kick something out. We need to kick a frame out. Say, okay, send it back to the hard drive. But here, a very tricky decision for us to make is, okay, which page should we kick out? So there's some choices. One choice is to terminate the current process. We terminate the current process and kick out one page. One strategy is that, okay, since there is not sufficient memory space, we just terminate this process. Say, okay, you have to wait because we don't have sufficient physical memory space for you. But this is not going to be fair to the user behind this process. Or the other choice is that we because the memory space is occupied by multiple processes. Now let's pick some other process and terminate that. Again, it's not fair for the user behind that process. So the best choice is to just do a page replacement, meaning that we kick out one page and bring in a new page. So whenever there is a page replacement, most likely there will be two page transfers between the memory and the hard drive. So in the first place, okay, we need to say copy the victim page. The victim page means that the page or the frame which needs to go out of the physical memory in order to leave space for the new page to come in. So so we need to send the victim page to the hard drive and then bring in the new page. Okay, so these are the two page transfers. However, if we think about this way, okay, so originally we have a copy of the victim page in the hard drive, so it's definitely going to be there no matter if this page is loaded into memory or not. So if we do not modify anything in this victim page in the memory, so by copying the victim page into the hard drive, we actually modify nothing in the hard drive. It's like we copy file A from memory to its corresponding place in the hard drive, and no, let me rephrase my statement. It's like, okay, it's pretty much like from you have a file and you create a backup file for it. So you don't modify the backup file, but you are copying the backup file, the content in the backup file into the original file. So nothing changes, right? So but this wastes time. So then people propose another way to save time, which is to set up a modified bit or dirty bit in the page table. So if this bit equals to 0, it means that this page has been modified since it was loaded into memory. So when we want to kick this page out, we definitely need to say copy the information from memory to hard drive in order to let the hard drive have the latest version of the file or the page. So or if its modified bit is 0, it means that this file has not been modified, so there is no need for disk write. So this saves time. And the overall page replacement procedure is here. So first, we need to find the location of the desired page on the hard drive, and then we need to find a free frame in the physical memory. If there is a free frame, yes, we can use it. If there is no free frame, we need to pick one victim and kick it out. But if the victim frames says a modified bit or dirty or the modified bit is 1, or if dirty bit is set, meaning that it's 1, then we need to write it back into the hard drive. So then we need to bring the new frame in, so and update the page table. So this is the procedure for us to do a page replacement. So then so there are two problems associated with demand paging, which means that so if we want to load pages into physical memory, only one is necessary. There are two questions needs to be answered. So the first question is that in a single process, how do we decide which page should be swept out, and also because our physical memory we need to load parts of multiple processes into the memory at the same time, into the physical memory at the same time. Then we need to decide, okay, how to allocate the physical memory to each process. So, and these two questions can be answered by two algorithms. The first one is called page replacement algorithm, and the second one is called frame allocation algorithm. So among these two algorithms, the page replacement algorithm is relatively more important. So okay, and let me talk about the first page. Let me talk about the first page replacement algorithm. It's called first come first out, or first in first out. Yes, if you remember the CPU scheduling algorithm, you should probably remember first come first serve, and actually they're the same. They're essentially the same thing. So first in first out meaning that whenever we need to kick out a page, we want to kick out the page whichever comes into the memory for the at the first place. So suppose here, okay, we have this one. We have the series of reference string. A reference string meaning that a string of the index of the pages that we want to refer to. So suppose that we only have a physical memory which can only hold up 3 frames. So we have 3 free space. At the first time when we want to refer to the 7th page, before that our physical memory is actually empty. There is nothing in it, so we have space. So we just load the 7th page into the memory, and then next time we want to refer to the 0th page. So we get then because we still have free space, so we bring the new page in. So we got it over here, and next time we just load the next referred page whose index is 1 into the memory. So but the next time, so we want to refer to the page 2, okay? But unfortunately, at the current time, there is no free space. There is no free space in the physical memory, so we need to kick something out. First in, first out, meaning that we want to kick out the page whichever comes in first. So among these 3 existing frames, page 7 comes first. So page 7 has to be kicked out, and then so we have space for page 2, okay? And then the next time we want to refer to the page 0. Fortunately, page 0 is already in the memory, so there is no page fault and no page replacement. And after that, we want to refer to the page 3, okay? If we look at the memory space, it has 3 pages, 2, 0, and 1. So among them, okay, 0 comes in at the first place. So we kick out 0 and bring in 3. And then at the next time we want to refer to the page 0, okay? So then we just say kick out 1 and bring in 0. And this process keeps going on. So remember, every time when we need to kick something out, we kick the page whoever comes in first. So in total, here we can just count how many page faults do we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 page faults. 15 page faults, and this number is relatively big. It's pretty obvious this page replacement algorithm is not very good. And then people design another page replacement algorithm called optimal page replacement algorithm. So the idea is that we want to kick out the page that will not be used for the longest time in the future. So here you can see that, okay, still the first 3 steps are exactly the same as the previous one, okay? So then at this time we want to refer to the page 2. It's not in a memory, and while the memory is full, so we need to kick something out. So now we have 3 pages, 7, 0, and 1. If we look in the future, okay, 0 is going to be referred very soon, and the next page in the memory that is going to be referred is 1. Okay, so we have 1 that is, and the among the 3 existing frames, 7 is going to be referred latest, so 7 has to be kicked out. So and this leaves space for the page 2. Okay, so this is the result we have. And next we want to refer to page 0. 0 is already in the memory, it's fine, no page fault. And then we want to refer to the page 3. Okay, so now we have 3 frames, 2, 0, and 1 in a physical memory. 3 is not in them, so there is a page fault, and we need to do page replacement. So among these 3 pages, let's look at which one is going to be referred which one is not going to be referred for the longest time. So 2 is going to be referred here, 0 is going to be referred here, while 1 is going to be referred here. So 1 is the page that is not going to be referred for the longest time. So we kick out 1 and we just load 3. So and then we want to refer to the page 0. Okay, 0 is already in the memory, it's fine. And then we want to refer to the page refer to the page 4. So unfortunately page 4 is not in the memory. So among the 3 existing pages, let's look at which one is not going to be referred for the longest time. So here we have 2 is going to be referred here, and the next one is among the 3 existing pages. 3 is going to be referred next, and the last one is 0. So we need to kick out 0 and bring in 4. So that's why we have 2, 4, 3, etc., etc. If you keep on this procedure, you'll be able to figure out the whole process. And here we can see how many page faults or page replacement do we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 page faults, which is significantly better than the previous first in first out policy. But unfortunately, and so first of all, it's guaranteed that optimal page replacement algorithm will yield the lowest number of page faults, and that is pretty good. However, according to the name, you probably can tell that this algorithm is not realistic in practice. This is because you don't know which pages are going to be referred in the future. Okay, and if you remember, the CPU scheduling algorithms, you probably will be able to relate it to one of the CPU scheduling algorithms that we learned, which are also the optimal ones, called shortest job first. So shortest job first is kind of like equivalent to this algorithm, the optimal page replacement algorithm. Yes, they are beautiful in theory, but they're not practical at all. And the last page replacement algorithm that I want everybody to be able to understand is called least recently used. So least recently used algorithm follows. So before that, okay, from the optimal algorithm, you can get a feeling that, okay, if we always swap out the page that is not going to be referred to for the longest time in the future, we can get pretty good performance, which means that we can get a very small page fault number. So and then the least recently used algorithm follows that kind of like idea. So basically it assumes that the page access pattern for a single process is stable. It means that if a page is rarely referred so far, in the future it's going to be rarely referred. Okay, so it's pretty much like if a person behaves pretty well in the past, we believe that this person is going to continue this performance in the future. Okay, so then the idea is that if we need to swap a page out, we swap the page which had which has not been used for the longest period of time. Okay, so here let's do the example again. So with these reference strings, the first steps are exactly the same. We have 3 page faults because none of them has been loaded into memory. Okay, so then at this time step, when we want to refer to the page 2, okay, so we need to decide, okay, which one we need to decide which page to kick out. Definitely it is 7 because the 7 has not been used for 3 time steps at this time. Okay, while 0 has not been used for 2 time steps, and 1 has not been used for 1 time step. So we just say kick out 7 and bring in 2, so which ends up with this result. And next when we refer to 0, okay, 0 is already in the memory, so there is no page fault. And next we refer to the page 3. So among the 3 processes, okay, let's check among the 3 frames, let's check which one has not been referred for the longest time. The last time we referred to is just right over here, okay, so which is pretty close. The last time we referred to 0 is over here. The last time we referred to 1 is over here. So among the 3 frames, 0 has not been referred for the longest longest time. Oh, sorry, I made a mistake here. So okay, so the last time we refer to 0 is over here actually. So 1 is the page which has not been referred for the longest time. So we just kick out 1 and bring in 3. So which ends up with this result. And next one we need to refer to 0. Okay, the page 0. Page 0 is still in the memory, so there is no page fault. Next we refer to page 4. Okay, we need to refer to page 4. And so definitely there is a page fault, and we need to do page replacement. Among the 3 existing frames, the last time we referred to 0 is over here. The last time we referred to 3 is over here. The last time we referred to 2 is over here. So 2 has not been referred for the longest time. So we kick out 2 and bring in 4. So which ends up with this. Okay. So and if you continue the procedure, you'll be able to figure out the next sequence. So in total, with this the recently used algorithm, we have 1 2 3 4 5 6 7 8 9 10 11 12 page faults. Okay, and if you are familiar with Linux, probably you know that, okay, Linux use this page replacement algorithm, LRU. So and LRU can be easily implemented by a stack. So I'm going to skip the detail because you are not going to implement that. And okay, sorry, there is one more say page replacement algorithm that you need to be familiar with, and highly likely it will be this algorithm will also show up in your final exam. It is called the second chance algorithm. So this algorithm is pretty much like round robin actually. So the idea is to associate each page with a reference bit. Initially we set the reference bit with 0, and if within a certain period of time this page has been referred, then we set it to be 1. So when we want to when we need to kick a page out, we need to decide, okay, which page should we kick out. What we do is basically in this way. Okay, say for example, if we are at if we look at a page whose reference bit is 0, we just kick it out. If we are at a page if we see a page whose reference bit is 1, meaning that it has been referred in the last period of time, so it means that this page is going to be referred relatively more frequently, so we want to keep it in the memory. What we do is that we don't kick it out, but instead we give it a second chance by keeping it in the memory while we set its reference bit to 0. So the next time when we are at this page, we swipe it out. Okay, so this is the way we do say second chance algorithm, how we do second chance algorithm. And there are also some other variations of the page replacement algorithms. For example, least frequently used and most frequently used, but they are not the mainstream page replacement algorithms, so I'm going to skip them. So next is the allocation of frames. The topic is allocation of frames. So this algorithm basically needs to answer a question. So suppose that we have 4 gigabytes of physical memory, and then we need to say load, for example, 20 processes into memory, and definitely the physical memory cannot afford to load all of them at the same time, so we only do demand paging. But the answer is, okay, how much space are you going to allocate for each process? So one way is called even distribution. Basically, we say we allocate, for example, so for example, if there are only 100 frames in the physical memory, and there are 5 processes, we allocate 20 frames to each process, and this is pretty naive. And the other way is called the other way is called proportional allocation, meaning that, okay, so if the virtual memory space of a process is large, is relatively large, then we allocate more frames to that process. So it's like everybody gets the same ratio of virtual memory loaded into the physical memory. Okay, and also there are 2 other replacement algorithms in terms of frames. The first one is called global replacement. It means that when we want to kick out one frame, we are free to choose the frames from all processes to kick out. And also there is another frame replacement algorithm called local replacement, meaning that for any process, if there is a page fault and there is a need for page replacement, we only kick out the frame of that process. And so, but in general, global replacement gives better performance. So the other a phenomenon with regard to the page replacement algorithms is called thrashing. Okay, so thrashing means this. Okay, if you only allocate a very small amount of frames or frames to a certain process, then the page fault can be extremely high. So this is the figure that describes the relationship between the degree of multiprogramming and the CPU utilization rate. As you can see that if we load a lot, starting from here, okay, if we load say a lot of processes into the physical memory, then our computer is going to be extremely busy with page replacement rather than letting the CPU executing the processes. So then this comes and this generates a phenomenon or observation called thrashing. We say a process is thrashing if it spends more time doing paging rather than execution. So this is a very succinct definition of thrashing. And this is because we allocate too few frames to this process, so it encounters a lot of page faults, so it has to do a lot of page replacements. And okay, so we can skip the next 2 slides, and then we can come to the next topic called memory mapped files. So Memory memory mapped files are I provide a program in that is at the same time with the slides to show what is memory mapped files. Basically, memory mapped give you the flexibility of mapping a disk block to a page in the memory, so that if you are modifying, if you want to say revise the file, just need to revise the page in the memory. And this is very efficient for file access. What it does is this. Okay, so if you look at the system call called mmap, it helps you to do this. Okay, so mmap allocates memory or map files into memory. If in the future, if you do a lot of C programming, you definitely have to be familiar with this system call, because when you encounter a segmentation fault, this is the way for you to inspect, okay, which part of your memory has an error. So to use that, okay, this function takes 6 parameters. ADDR means the address of the memory. Which address of the memory we want to do a map, and then it is the length of the memory. And for prod you can skip that, and then flags also you can skip it. FD means the file descriptor, or you can take it as the file ID, and offset meaning that, okay, so starting from which place of this file do you want to do a map with the memory. So here I provide a program to do that. First, you can see here, okay, first we just by opening a file, we get the file descriptor, so which is the file ID. And then next we build the mapping. Okay, so we want to map the 0 space of the physical memory into with the file, with the start of the file. And then we want to print out. So this line is relatively important. We basically read the file from the memory instead of from the file itself. So let's say what is the output. When we execute the program, we see the output is over here. So basically it prints out the whole file. Yes, but it's from the memory instead of from the file. Okay, so in summary, this is the content that we have gone through so far, which includes page replacement algorithm, allocation of frames to process, and thrashing and memory mapped files. So let's take a break and come back later.